Thank you, Tom. It's my pleasure to introduce the last session today at the 15th MIT CDOIQ event, and my friend and colleague, Dr. Arka Mukherjee, is going to have a conversation with us. I want to introduce him, though, because if you don't know a little about his background, it helps to understand who he is as a person. First of all, he's got 3 degrees, which makes him one of those FUDs like the rest of us. He studied intensely chemistry for a number of years, and I think that you'll see from the products that he's developed over the years that has influenced his thinking in this area. He is a strong supporter of the education component that we need to have here. If you've listened to me at all, you know I rave about how little we're doing in education, how much more needs to be done in these areas, and he's been one of the strongest supporters on that. After a career with KPMG and Accenture, Dr. Mukherjee became a principal at IBM and stuck around there for a while, and then had this vision where he's going to go out, and he's not quite like a Mark Zuckerberg kind of thing in the sense that kind of a vision, but he's been working on implementing this idea of data lineage at a number of enormous companies around the world: AT&T, Walmart, United Healthcare, Morgan Stanley, HBSC. It's just, people are really understanding and enjoying this. And in some ways, Arka, at those organizations, you're kind of preaching to the converted, but here I'm guessing most people are not familiar with this. So as we go forward with the conversation, please do drop your questions into the Wahova platform, and we will get to as many of them as we possibly can. But with that, Dr. Mukherjee, I will turn it over to you. It's so good to see you, sir.
Thank you, as always, Peter. You're always too kind. So, I will just mention, just as a sidebar, I've been working on the educational side as well. And so, Peter, you've been an inspiration for all of us in terms of just working with the educational sector and building out the data area. So we are all privileged by your presence here. So,
well, thank you. You're too kind.
So, okay, so we're going to talk about sort of data lineage today, and we'll introduce the problem. I spoke on the same topic in last year's session, but I want to go into some more depth right now. I'm not sure whether that was the right decision or not, because it's the last session of the day, and this is a pretty heavy technical topic. But nevertheless, we'll give it a shot. And Peter, please provide me some feedback in terms of whether I should keep it at a reasonably high level or go deeper. Your opinion would be appreciated.
We're already getting questions popping up in the chat, so jump right in, and we'll keep it focused as we can.
Lovely. Okay, so we'll start in introducing the topic of data lineage, and then talk about approaches that work, approaches that don't work, and then really focus the session today on the issue of proof. Right? And this is a topic that's sort of rarely addressed, but from my viewpoint, a pretty important one. So we'll go into like 10 types of proof that make data lineage a trusted way of improving the enterprise data ecosystem, and then we'll talk about some outcomes of what this might imply. So just briefly about myself, Peter has already spoken to me, spoken about my background, so I'll skip that. But I will give myself a pat on the back for perseverance. Right? So we've been working for now 20 years in trying to address a set of important problems in data management, particularly those related to understanding data ecosystems. And the data ecosystem problem is a problem that's a difficult one, and you have to devote a lot of time, energy, and money in order to address it. But the idea is we are asking about, yes, there are many important problems that come from looking at silos and trying to solve problems within silos. But the question that we're asking is, but what about the whole? Right? There are problems that come from looking at the whole ecosystem as well. And these problems are very hard and rarely tackled. But we've been peeling the onion, so as to say, for the last 20 years. in order to systematically understand the holistic way of managing data for a data ecosystem. And we have implemented inside some of the world's largest companies. So Peter gave some examples, but these environments are truly very large, where you don't have databases in hundreds of thousands. You're dealing with tens of thousands or hundreds of thousands of databases. Right? So we are trying to bring large scale automation, hyper automation, in terms of managing data in those environments. We don't have a lot of customers, but we do have strong relationships with the customers we have. And essentially the idea here is to bring in hyper automation in some of these problems. The problem that we've recently focused on is the problem of data lineage and the one of graphs. And that's what we're going to talk about today. So what is our aspiration here? Right? The aspiration for global ideas is that when we encounter organizations, we see a very large amount of unorganized data, right? And the unorganized data is like everything sort of thrown into an environment or an organization has evolved, and they've just like thrown data into various kinds of storage areas, and it's disorganized and it's not it's hard to work with. It's like having a garage full of stuff. You don't really know where to start in terms of looking at the information there. So when Global IDs starts looking at this unorganized data, we say, okay, yeah, here's data about, like, let's say orders, right? And here is data about customers, and here is data about products. And so it's in this garage with data strewn all over it. You have a variety of different kinds of data. And there's all this data sprawl that has existed. This is typically the environment in the majority of the customers that we work with. And I would venture to say that those organizations that are getting into data management see this, and this is a familiar situation. But the idea over here is, can we organize the data? So can we essentially take each piece of data, put it in its right bucket, so as to say, in the right part of the taxonomy, the right part of the ontology, the right data model, and then can we then create knowledge planes out of it? What does a knowledge plane mean? So knowledge plane means here's a cube of data, or I wouldn't say a cube, but it's a plane or a view into the disorganized data landscape, where you're looking at a specific way of looking at data, and that's we're calling that a knowledge plane. And so knowledge planes can then be extended into a whole bunch of different areas. But one way of looking at it is that most customers, right, or most of the data environment actually does exist in knowledge planes, but it's all been mashed together, right? And what we are trying to do through software is separate out each of the knowledge planes into distinct semantic categories. And the distinct semantic categories now give us a way of sort of tackling each knowledge plane without getting distracted by other information from other knowledge planes. So if you ask me, okay, give an example of what is a knowledge plane, we'd say, let's take a look at something like a customer, right? And you separate customer information from product information, from supplier information, from employee information, maybe 100 to 200 dimensions like that, that you normally encounter as dimensions in your data warehouse environment. But those would be approximate ways of representing knowledge planes. And the advantage of looking at all these dimensions through these knowledge planes is that you can start building graphs on top of it. Now, graphs, as many of you may know, is a very sophisticated way of modeling data. For the last 50 years, we've been modeling data in entity relationship diagrams backed by relational databases. There have been evolutions in the database environments as well, but we've missed the fact that everything is interconnected to everything else, and graphs essentially solve the problem. That while in relational databases, a large number of relationships cannot be explicitly put in, or it's more difficult to put in graphs, it's very easy to put this together. And of course, the W3C has been working on the semantic standards for almost 20 years now. And so knowledge graphs is sort of the future of bringing large-scale automation. So we've gone that way, and we've created we started building sort of metadata knowledge graphs, data knowledge graphs, value knowledge graphs that essentially take these different knowledge planes, put it into knowledge graphs. But once we have the data in knowledge graphs, we essentially can answer any question that's within that knowledge plane. And so it points to a direction where you can use large scale hyperautomation against the knowledge graphs. So we've been spending a lot of time trying to build out knowledge graphs according to these knowledge planes that form the foundations of most organizations' data environment. Of course, the idea here is not just creating the knowledge graphs, but to support different kinds of analytics that are not currently available. So relationship analytics, that these knowledge graphs have many more relationships than exist in the relational environment. And so by having a richer set of relationships in the graphs, one can do relationship analytics better. One can look at change better because you can feed billions of triples into a knowledge graph or a graph database. And so you can observe change very, very fast as well. You could do lineage analytics, which we're going to talk about today. We're going to talk about sort of master data is the knowledge plane analytics that we're talking about. And then there's, of course, problems like large scale reconciliation that can be also addressed in this particular way. So this is sort of our vision of intelligence at scale with large scale hyper automation built in. And what we are essentially trying to do is to say that if you really want to implement AI ML, you need to get the semantics right, and that essentially you can do hyper automation on things like integration, hyper automation on things like quality, and hyper automation on things like analytics. Right now, I have to say that like the AI ML part is sort of an aspirational state, right? But many of the other things we have had successful implementations in. And we feel very optimistic about this direction because it says that difficult problems like data lineage are actually tractable. They're not intractable as they are as currently presented. So I've laid out sort of the aspirational state. What is the actual state? And what is the science behind it? So the aspiration, so in terms of the actual requirement by organizations, they say that, look, I understand my static data environment. This is all the data assets I have. I can govern it, etc. But where does the data originate and where does it flow to? And so the idea here is that understanding the flow of data across the ecosystem is a first derivative problem, I would say. It's the change in time. Right? How does data change in time as it moves from one place to another? So it's the first derivative problem. And the first derivative problem is, okay, what's moving? What are the parts of the system that are actually changing and moving? What are the relationships that are, again, changing and moving? And then, how do I sort of order everything in time so that I get a flow diagram at the end of it? And so bottom line is we need to understand how data changes over time, how data moves over time, and how data evolves over time. And so that is, in essence, what a lineage diagram, data lineage problem looks like. And the intellectual frame that we use in order to sort of understand data lineage, of course, is what I had described a little bit earlier, which is the idea of sort of separating out each of the knowledge frames that are involved. So if you look at the picture on the left here, before you have lineage, you have a lot of information in a lot of different systems. And in these systems, everything's sort of mashed together, right? But after data lineage, you have the customer data traveling on its own trajectory, the trade data, the loan data, the order data, and so, another 100 dimensions, sort of traveling on their own tracks, so as to say. And so instead of looking at this complicated mess, you've actually isolated each area, and then you're looking at each of these knowledge brains with their individual data lineages separately. Right? So this is the intellectual framework, and then if we go to the idea that, okay, it doesn't seem like a big deal, why is why are people really interested in this problem? So of course it's a hard problem, because these first derivative and second derivative, the acceleration problems, are essentially have a variety of difficulties associated with it. The most important one is the one that I mentioned earlier, that data itself is disorganized, so you can't actually parse out separate kinds of information together. It's all mushed up, and so it has to be organized first, and so lineage is harder. Of course, most lineage projects nowadays is done sort of manually, so it's associated with fairly high costs and slower delivery. So these things make it a little bit harder. And what we have figured out after 5 years of largely failures, right? 5 years of failures is a pragmatic approach towards actually solving the problem properly at scale. And essentially, the way the pragmatic approach works is that you first identify your data by fingerprinting it, right, and making sure that all your core data assets have fingerprints associated with it, and these fingerprints can be matched with each other to know where the same data exists across the ecosystem. So if we look at once we have identified the data, we say, okay, the same data exists in these databases. How does it get there? And so the software, we use the software to generate hypothetical sort of flow segments. So it's a hypothesis of how data got from here to there, right? And so for each place where we find a piece of data, we say, this is a hypothesis of how the data has been moving from here to there. Because I'm assuming that we don't have access to the code, right? So in most of the cases, certainly for environments that are very large, like the ones I mentioned, the code associated with the data movement is not available, rarely available, to say. And so we can't really rely on scanning code in order to do that, though we have the capability to do that, but we just find it hard to access the code. So we are looking at source and target environments and trying to figure out if there is flow. There are problems with that approach as well, which I will mention later. But the idea is to generate hypotheses, right? And then we let either humans or machines validate each segment and provide proof. And once that proof is created, then we generate reports and dashboards. And this approach we have found to be very pragmatic, solvable, addressing the limitations of most customer environments. And it's low touch, very minimal kind of touch, doesn't interrupt anything, and is pragmatic in terms of trying to solve the problem. So at the end of it, we get something like this. We get a flow diagram. And the flow diagram says that, here's a report at the end of it, right? Maybe perhaps it is a regulatory report. These are sort of must-have use cases that organizations have. And so here's the regulatory report. How did the data get there? And can I trust it? So, and a diagram like this is being generated. And the diagram essentially says, here are all the tables. This is the sequence in which they move through the data ecosystem. and this is the data that lands into the regulatory report. So the end state of a lineage diagram, a lineage project, is a bunch of diagrams like this that have been validated and trusted, so that you know that the data in the final report, where it came from, and that you have ways of knowing knowing the flow and the path of data across the ecosystem. So this is where we left off in last year's MIT session, saying here is a pragmatic approach, and here is how a lineage flow can be attempted. So in the year that has gone by, we've taken it a little bit further advanced and says, well, this is really not enough, right? So when we look at a diagram like this, and there's an arrow that flows from one table to another table, how do we actually know that that's true, right? And so our demand for evidence and our demand for scientific proof essentially led us to creating a bunch of things that we're going to talk about now. But the idea here is, how do we know, right? And I'll give you an example of just by looking at a video over here. Peter, let me know if you can see a video screen. Okay, I guess you're on mute.
Yes, you're ready. You're all set. Click play.
Okay, lovely. So here, just to say that I want to trace a particular record as it flows across the system. So I'm doing a search for a particular record related to a particular account holder, and I'm saying, okay, that particular account holder's records, how did it move from system to system? So the software is observing the transaction and saying what are the timestamps associated with it, and can visualize the flow. I think there might be a little bit of the lag in the video right now. So so I'll just pause this for a second and say that essentially what the software is trying to do is to look at temporal data overlap. How does a particular transaction with its timestamps move from system to system, and now you have a visualization that is able to sort of capture the whole thing and put it in this visual representation. So if I continue with the video, so now I've added, in addition to the transaction ID, I've added the account holder ID, I've added transaction IDs, and so now we can see related information, both transactions and account holder IDs sort of moving at the same time, and how the information is sort of split and aggregated across different kinds of databases. So so you can keep doing this and taking related information, but of course one can also look at the actual records inside each of the systems and say, okay, this is the system, this is the record in system 1, this is the record in system 2, and I have actually validation that individual records from each of the systems is what is leading to this particular lineage. But the idea is that once we call this the step beyond data lineage, which we call the data traceability, where individual transactions, individual records are flowing across the system, and the software is able to track it as it flows. So yeah, so I'll just finish the video over there, and just shows the various transactions at various points in time, moving across the system. So okay, so let me now go back to my presentation. Okay, so lineage followed by traceability is what allows organizations to say, okay, now I know where the data came from and where it went to. So so this ability to trace individual records is sort of the end state of a lineage project. Now, the core question that we are going to address now is, what is the burden of proof here, right? How do we know that all of this actually happened? Right? I showed you a data lineage flow diagram. Why would you believe me? Why would you say that this is actually right? That didn't come out of your imagination, and you drew lines on this particular diagram. How do we know that all of this is true? Right? So when we uh, ask for scientific evidence in terms of how the data is flowing, we say, well, each arrow that's in that particular lineage diagram has to be supported by evidence. So that's at the granular single arrow level, and there has to be evidence. And then in aggregate, all the arrows are also supported by evidence. Right? So at the granular level and at the aggregate level, each of the arrows in the flow diagram have to have evidence behind it. Um, and then, okay, so you say, okay, great, that makes sense. How do you prove this, right? And the way we prove this is uh, right now, right, is that there's subjective evidence, right, which we call the human attestation method. And then there's objective evidence, which is the data-centric validation that we tend to prefer. But the human attestation part is oriented around a user of the data going in and said, well, I've been working in this organization for 20 years now. I know that this is the way data is flowing. It's flowing from this system to this system to that system. And I attest that this is how information is flowing. Now, of course, so you could say, okay, I trust you and be done with it, right? But if you take the principle of trust but verify, right? The second part, the objective evidence part, is the verification part, right? Validation and verification of the data flows, and we tend to trust that part more because it's actually based on data in the systems, right? So the proofs that I'm essentially going to show you are 10 proofs that are oriented around saying that I, I'm using a scientific objective method to actually show that my lineage diagram is true. Right? So that's what we are attempting to do here. So to just restate the problem again, um, I have a diagram that looks like this, and it all looks pretty nice and visually appealing, and looks essentially possible. But I want to provide you evidence that each of these arrows, the blue arrows, the green arrows, the black arrows, right, fully backed by incontrovertible evidence behind it. Right? So, okay, so that's how we answer the question of how do we know that this is true. Okay, so there are, as I said, we are going to go through 10 proofs, and we're going to go through it somewhat rapidly, right? But the first area of proof is the proof of existence, right? That that essentially we want to show that there's common physical metadata, there's common logical metadata, and common semantics, right? So these are proofs of existence that the data in system 1 and the data in system 2 have the metadata in common, right? So that's the first set of proofs. Second set of proofs is proof of overlap, that there's data overlap between columns, there's data overlap in timestamps, there's data overlap in records, right? These three things essentially give us evidence of proof of overlap, where once you can establish that kind of overlap, you know that there's additional evidence. Still not overwhelming evidence, but increasing probability that there is overlap and there is flow. And the last part, which we think is sort of definitive, is the proof of reconciliation. Can I reconcile the data for records in both across all source and target systems? So I have, I can have reconciliation at the column level, I can have reconciliation at the record level, and I can have reconciliation at the value level. to provide increase the probability that yes, this flow is happening. There's also a 10th step over here, which I'll mention briefly at the end, but that's the end-to-end reconciliation of the entire graph, so as to say. But let me just go through these individual proofs and give you a sense of so what these proofs are. So proof number one, right? I've made a claim that my data flows from application 1 to 2 to 3 to 4, right? And so I have to essentially show that my physical metadata for all these columns that are in these various systems are actually the same thing, right? So the physical metadata should say that we are dealing with the same kind of data, or same kind of physical data across these different systems. And so as we look at this, we have some idea that okay, it's actually the same metadata. I'll skip sort of how we do this through the software, but that part should be sort of self-evident. In this particular diagram, we're just showing that here's I'm tracking customer information, so all the customer IDs should be the same in the various systems that we are claiming to be a part of the flow. Proof number two, right? Existence of logical metadata, right? So I have data moving from application 1 to application 2 to application 3, and I need to make sure that the right logical metadata is associated with all the data as it moves. So in this particular case, I might have one of the fields might be a national identifier. National identifier might have a whole bunch of variations associated with it, but at least if it's the same logical field that I'm saying is moving, then I know that there's a higher probability that all of this must be true. So I just increase the probability bar for having common logical metadata. Once again, there's a screenshot that essentially shows that the idea of a customer ID, and customer ID may have a whole bunch of different variations, but I'm looking at the same logical metadata as it's flowing across across a variety of different systems. So now we move into proof number three, and proof number three is the existence of common semantics. Now, this we think is very, very important, right? Most lineage efforts, at most, they try to sort of match up the physical and the logical part. But if we ask, Sir Tim Berners-Lee at W3C and all that, said no, physical and logical are, the logical part is a human understanding of the data, and the physical part is a database understanding of the data. Neither of these are authoritative. What is truly authoritative is the semantic understanding of data, right? So what we try to do is to put essentially all the data in the right semantic bucket and say those right semantic buckets are flowing across the system. So if you look at, let's say, something in this case like a national identifier, or these different semantic buckets that are indicated on the left, we can see that we can see that they are mapped onto different categories of information in the various databases that we are looking at. So common semantics is again a very significant part of proof, because it removes the ambiguity associated with the movement of data. And once you have data, the same kind of data with the same kind of semantics that's moving, you have further confidence that the lineage diagram is true. So these are sort of proofs of existence of common semantics. In this particular diagram, I have shown that in both source and target columns, I have the same semantics. So it's called customer ID here, it's called customer code there, but it has the same semantics, and so I can draw a line between the two areas. So So when I then visualize the same information in a different way, I can then show it side by side, and I'll wait for the a picture to refresh on the screen in order so that you can see it as well. So here's sort of what I'm talking about. I've drawn a line between a customer code and a customer ID, but because they have the common semantics, I know that this is true. I move to the next set of proofs now, proof of overlap. And
Okay, let me interrupt for just a quick second here. I'm so sorry. We're running out of time, so we've got about 2 minutes left, and I didn't want to. I wanted to ask you specifically. There's a lot of really good questions in the Q&A, and I wonder if perhaps we might craft another webinar series. I hate to go outside of the protocol here, but they're really, they're basic questions about profiling and what do we need to do to create a business case for this type of idea. Could we arrange with you to do a follow-on broadcast in our ISCDO webinar series and address these questions specifically, because they will be very illuminating in this conversation here that you're having. And I know that you've got lots more evidence of this. I don't have to tell you guys, this stuff works because Arka actually built it using the technologies that he's using to do this. So it's the case of the cobbler's children having perfect sets of shoes in this case. Again, more technical stuff that we just can't get into here. But I wanted to leave the last 2 minutes for you and assure everybody here that we will work together. If you guys will actually just reach out directly to me, I'll put you on the list for when we're going to try to reschedule this second dive in here. And Arka, I'm just presuming you're okay with this. I'm watching you, and thank you so much.
I welcome the opportunity, and I may have spent a little bit too much time on the introductory part, but essentially, I'll just go through these slides very, very rapidly in a minute, and say that if you have overlap between data, you have further proof of validity of the lineage streams, and there's overlap of data timestamps as well that leads to further evidence and further proof and further validation of the overlap. So Peter, I would say that I will cover this in much more detail if we get a little bit more time associated with it. But yeah, maybe if you want, we can answer sort of one of the questions. That might be
the one with the most votes is asking what would be an efficient approach in capturing data lineage in an automated manner. Most solutions available need manual input from data architects, modelers, or data governance personnel. Gosh, I think you addressed that perfectly in there. So maybe.
Yeah. So the idea is, software can be used to automate data lineage, which is of course what we do for a living. And there are a whole bunch of good companies that also attempt to do that. And so it is possible to automate the generation of the flow diagrams, and then use either humans or machines to make sure that the flows are indeed correct. And some of the things that we are showing you are proofs of how you establish the correctness of the lineage diagrams.
Arka, again, apologize for running out of time here like this, but please, if you all will definitely reach out to either Arka or myself, we'll put a list together and tell you when we'll do this follow-on piece, because I want to get the answer to these very good questions on the record with you, in the sense that it helps to go back into some of the thinking that you had as you put the whole architecture together around this. So Arka, thank you so much for doing this. We hate to run on this, but we do have to stick with time constraints, and we will be back in touch. So my address is peter.aiken@vcu.edu, or any of the other things out there. Arka is fairly easy to find as well. Click on his page in the Wahuva app, and we will thank you all, and hopefully see everybody first thing tomorrow morning.
Thank you very much, Peter.
Thank you, Arka. Always a pleasure.
Bye.